Question 2.1. Suggest how the design ensures that there is no deviation of the ray as it enters the first prism. Here's the first prism, and for the ray to enter without any deviation, it has to go through the normal line. The normal line is the line perpendicular to the prism, to the boundary of the prism. Here's the boundary and here's the normal line. So the ray will come along the normal line and then we'll be able to go through. Question 2.2 says that suggest two features of the design that ensures that there is no deviation of the ray as it leaves the first prism and enters the windscreen. Well, as the ray leaves the first prism, we have to make sure that we treat each point independently. 2, the prism material will have same refractive index as the windscreen, and the prism fitted to the windscreen without gaps, because a gap would mean another medium between them. Question 2.3. The refractive index of the windscreen is 1.52. Explain why the ray follows the path shown inside the windscreen glass in figure 1. Support your answer with a suitable calculations. Well, so the ray obviously has to go in at right angle, and because it's going at right angle, that angle of the right angle is 90 degrees. Applying Snell's law, the Snell's law equation is this. Rearrange that, and the angle of glass is there and an angle of air. So we got the sine of angle of air, which is sine 90 degrees, which is 1. Refractive index of air is 1. The refractive index of glass is 1.52. That's given in the question. Making the sine of the angle of the glass the subject and substituting these values in, we got that. Then divide both sides by sine. We get theta equals sine to the power minus 1 over 1.52. And the glass, the angle of the glass of theta is 42.1. But that's the critical angle there. So 42.1 is the critical angle. So that's the critical angle there. And because 45, entering at 45, which is now greater than the critical angle, results in a total internal reflection. That's total internal reflection at each boundary. So that means that to get total internal reflection, it has to be the angle of the glass has to be greater than 41.1 degrees. And this is what happened because we got 45 degrees. So that's definitely greater than the critical angle. Question 2.4. When it starts to rain, water droplet from the outside of the windscreen as shown in figure 2. Explain why the presence of water at A causes the intensity of the light of the detector to decrease. Support your answer with a suitable calculations. So we know the refractive index of glass is 1.52. Now the refractive index of water is 1.33. Again, using our Snell's law, we've got the sine of the critical angle over sine of the angle of 90. That's what we want. So that critical angle here will give you the 90, and that equals N2 for air over N1 for the glass. So we know sine 90 is equal to 1, and rearranging this, 1 times that will be that, and then dividing both sides by sine, or sine C, or sine of critical angle is equal to that, and then divide both sides by sine, we get sine to the power minus 1. And then that gives us sine of the critical angle, or the critical angle to be 61 degrees. And since the critical angle is now 61, but the angle we're using is 45, which is less than the critical angle, therefore total internal reflection will not occur, because for total internal reflection to occur, the angle we're using must be greater than 61 due to the water. So the light is reflected out. Intensity of the light, that means it's going out there rather than going into the glass. So it's going out there. And therefore, the intensity of light reaching the detector is reduced. So some of the light is refracting into the water. There's water there. Don't forget that we do have partial reflection making into the detector still. That's a partial reflection, not refraction. Question 2.5. The refractive index of the windscreen glass can vary by a few percent across the thickness of the glass. Discuss how this variation may affect the path of the ray through the windscreen glass. Light may change direction inside the windscreen. It may change direction at the windscreen boundary. Variation is too small to deviate significantly within windscreen. That will be the internal effect. Variation too small to affect the total internal reflection at A without droplet. That's the boundary effect. So you can choose any two from this question. Question 2.6. A different design has the LED and the detector further apart. The ray undergoes more reflections inside the windscreen glass before reaching the detector. Discuss two ways in which this different design affects the sensitivity of the sensor to the presence of water droplets. So the two ways, first way is to talk about a more sensitive because more likely to encounter or detect water drop or will encounter more water drop. Bigger decrease in light intensity as you have more water drops, so more sensitive to rain. 2, this time we're talking about less sensitive because more likely to encounter imperfection in glass surface, such as dirt and scratch. Any curvature effect will be greater, so may not hit detector. Light intensity reduced without presence of water. Therefore, you get greater absorption in windscreen due to greater path length. For more sensitive and less sensitive options.